Okay, so welcome to section 3.2, which is arc length, which we've already kind of done a bit of in section 3.1. So arc length, velocity, and area. And these are all going to pertain to circles. Okay, so let's recall that arc length was what? Arc length, S, was radius r times angle theta, where theta was necessarily, where theta is in radians, not degrees, because you can't have a distance or a length that's in degrees. That makes no sense. Okay, so let's note. Can I have a distance that's in terms of radians? Well, yeah, because a radius is a distance. So it's just one distance with respect to another distance. So to that effect, radians are unitless, meaning they don't have that degree symbol or a foot symbol. They're just radians. So radians are unitless measures, which means we can use them for a lot of things. Unitless measures or measurements. They are very convenient. That is, i.e., it is n radians. So say we have n radians is equivalent to, so 3 equal signs, some number n in the real numbers. So n is an element of the real numbers. So let's also recall, if you're going down the freeway at 80 miles per hour, that means in 1 hour you will have gone a distance of 80 miles. So we can think of velocity, linear velocity, v, let's call it little v, as distance, how many miles you went per hour, so over time. Oops, why does that autocorrect to such a strange place? So distance over time. And we annotate that by, of course, s, the length over the time, because now we're dealing with circles, right? So our length or distance is s and our time is t. So let's consider a circle. I'm going to draw a circle if I can. Please autocorrect. Yes, thank you. Okay. So we have our circle here, and maybe the circle is turning. And much like we like to measure our angles counterclockwise, let's also assume that we're turning counterclockwise as well. Okay, so circular movement. We're going in circles. So circular movement. We don't have a linear distance. Do you agree? So what is wrong with me? Circular movement. Is termed, well, it's not the same as normal velocity because, like I said, we're not moving forward in space. We're just going around in circles, quite literally. But your circle could be spinning very quickly, like the wheel of a car, or very slowly if you're just taking a short ride on your bicycle, or maybe you've got the wheel of your bicycle off the ground and are just turning it very slowly. Notice your bike isn't going anywhere, but the wheel is turning. And the term for this type of velocity is angular velocity. So angular velocity is when you're just going nowhere but turning, sitting and spinning, as it were. Okay, so we call that omega, and that's going to be the angle not distance. So we want angle. How much of an angle have we gone through per unit time, so per hour. So that's going to be theta over t. And of course, since it is a velocity, we make sure that theta doesn't have degrees attached. We want it to be unitless, so theta will have to be in radians, because we can't have a velocity in terms of degrees. That makes no sense. Okay, so let's note something. Note. So we have that arc length s is radius r times angle theta in radians. Okay, so what does that mean? That means if I isolate theta by dividing both sides by r, I can say theta is arc length s divided by r. Okay. Well, let's go ahead and divide both sides of this equation by t. So I'll get theta divided by t is going to be equal to s divided by rt. Let me keep the r in green, and we're dividing both sides by t. Okay, well, theta over t is omega, right? So this is omega is equal to s over rt. Okay, let's keep that for the moment. S over rt. What I'd like to do, I'd like to multiply this whole equation through by let's multiply this by r. And there's a reason I'm doing this. So I've got r omega on the left. R omega on the left is equivalent to the r's reduce on the right, and I'm left with s over t. Okay, well, did that help me at all? Well, what is s over t? S over t is velocity v. So that's just velocity v. So r omega, radius times angular velocity, is the same as linear velocity. So now we have a theorem. Let me do this theorem in light purple, I guess. It's a theorem that we just derived by using a whole bunch of equivalences. So angular velocity, omega. So angular velocity, omega, is equal to theta over t. Oh boy, that's a terrible t. Let me write that better. Theta over t, where, of course, theta is in radians. And linear velocity v is equal to r times omega. Okay? So for example, so let's find the angular velocity. So find the angular velocity. The angular velocity, remember angular velocity is the circular one, so that's omega. And linear velocity, and linear velocity is a velocity we know from miles per hour, so linear velocity of a ball in a circular cat toy, cat toy of radius 6 inches. So comma, if it takes, how long shall it take? If it takes, let's do 3 seconds for the ball. To go around the circle. Let's say 5 times. 5 times. And anyone who has a cat will know exactly what toy I'm talking about. Okay, so anyways, so find the angular velocity. So we want to find omega. Actually, let me have omega be a different color. Let's have it be blue. So omega will be equal to theta. Well, we've got around the circle 5 times. That's all I have right now. Divided by time. Let's have time be in purple. T. And do I have T? Yeah, I have 3 seconds, right? Okay, so theta over T. Okay, so omega will be, notice I don't have the radius here. Angular velocity is going to be, I go around a circle 5 times. So I claim that this will be 5 times a full revolution. That's 2 pi, right? So, and I'll state why in a moment. And this is 3 seconds. So off to the side, let's say, because 1 revolution equals 2 pi r, and we have 5 revolutions, right? 5 times. Okay, so I claim that my angular velocity is 10 pi over 3. Yeah, 10. 5 times 2, 10 pi over 3 units per second, radii per second. Okay, hertz, I suppose. Okay, well, that's my angular velocity. So I need to use that to find my linear velocity. So linear velocity v, I know is just radius r, which I don't have yet. So let's do, what color shall I do? Let's do, so radius, 6 inches. So I know it's radius times omega. No, bad color. Let's choose this color, radius, 6 inches. So r times omega. So I claim that linear velocity v is going to be 6 inches times omega, and we found omega was 10 pi over 3. Okay, well, 3 goes into 6 twice. So I claim that the linear velocity, meaning miles per hour, will be 2 times 10 is 20 pi. And that's units per second. Okay, so that's how we relate angular and linear velocity. I'm not a big fan of applied stuff, so let's go back to theory, shall we? Okay, so let's recall. What's the area of a circle? So the area of a circle is pi r squared, right? Pi times radius squared. Okay, and what about 1/2 the area of a circle? Well, I could just take the right-hand side and divide it by 2. So pi r squared divided by 2. Okay, what about 1/4 the area of a circle? Well, just take the original area of a circle, pi r squared, and divide that by 4, etc. We could do 1/8 the area of a circle. 1/8 the area of a circle. And we could do this on and on. Oops, So that's going to be pi r squared divided by 8. And we could go on. And we will. We're actually going to come back to this. But let's note something. So leave yourself room on the right-hand side there, because I'm going to note. So what I'd like to do is have at least 3 little x and y coordinate axes. 1, with a circle. So we're going to have 3 of these. Let's go ahead and do a circle of radius 2 if I can do it. Autocorrect. There we go. Okay, so let's copy and paste this. Copy, paste. So 2. Copy, paste. 3. So 3 should be good. Okay. So if I look at the whole circle, meaning my angle here, so let's have theta for a whole circle, would be 2 pi, right? So I know if theta is full circle, and the area of a full circle was pi r squared. So area is pi r squared. Okay. Well, I could think of that as 1/2 of 2 pi, because the 2's would reduce r squared. Okay, that's interesting. So that would be the area of the whole thing. So shade in the whole thing here. We want the whole area of this whole circle, right? Okay, now let's look at let's do half the circle this time. So my angle theta, I'm just going to subtend half the circle. So that's half of 2 pi, so theta is just pi. So now I want to find the area of just the top half of the circle. Let's see, let me put my... So I want to know what the area there is. Well, the area is going to be 1/2 of pi r squared, right? Oh, well, that's interesting. I could write this as 1/2, oops, equals 1/2. I could write the pi in purple, and then r squared. Okay, let's do another one. Let's do the 90 degrees. So let's have theta just go from 0 to 90. So theta will be 1/4 of 2 pi, so that's going to be pi over 2. And the area yeah, I didn't color code very well. Sorry about that. So we want now the area of 1/4 of a circle. So the area of 1/4 will be pi r squared over 4. Well, let's factor out 1/2. So what's going to be remaining there in order to get 4 in the denominator would be pi over 2 r squared. Okay, so basically what's happening here is if we factor out a 1/2 for each of these, so 1/2 times 2 pi r squared, and in the next one, let's factor out a 1/2. It's 1/2 times pi r squared. In the next one, if we factor out a 1/2, it's 1/2 times pi over 2 r squared. And here, if I factor out a 1/2, it's going to be times pi over 4 r squared, where in each of the cases, this corresponds to the angle theta, 1/2 theta r squared. That subtends that much of r, so 1/2 theta r squared, 1/2 the theta, angle theta r squared, 1/2 the angle theta r squared. Notice that's what we have here, 1/2. And each of our angle thetas times the radius squared. So the area should be, if we did this correct, what should our theorem be? Let's do a bit darker purple. So the theorem should be as follows. I claim that the area of a sector, so let's let theta be a central angle, meaning its vertex is at the center of a circle, usually at 0, 0. Be a central angle given in radians. Given in radians. On a circle of radius r, so on a circle of radius r. Then the area of a sector, and what do I mean by sector? Let's look up at the pictures I did. It's really a piece of pie. Notice this is the whole pie, this is half the pie, and this is a quarter of the pie. So think of a sector as a piece of pie. So then the area of a sector, do you know what? Let's use the sector. That sounds better. And the area of the sector, subtended by an angle theta, is what? The sector subtended by theta is given by, well, in each of these cases I saw that area was 1/2 the angle theta times radius squared. Now usually we call it 1/2 r squared theta. It's the same thing, 1/2 r squared theta or 1/2 theta r squared. Doesn't really matter, but you'll see it in your book as 1/2 r squared theta. Okay, so for example, so let's find the area of the sector of a circle. So find the area of the sector of a circle, the sector of a circle, subtended by let's have theta be 7 pi over 6 radians. On a circle of radius, what shall we do? Radius r is equal to, let's have it be 8 feet. Okay, so I want the area A. So I know the area A is going to be 1/2 radius squared times the angle theta given in radians. Okay, so let's see what I have. I've got my radius is 8 feet. And do I have my angle theta in radians? Yes, I do. Okay, so all I have to do is plug in. So I claim that the area of the sector subtended by that angle on that circle is going to be 8 squared, 7 pi over 6. Okay, so 8 squared is 64. So 1/2 times 64 times 7 pi over 6. Okay, does 2 go into 64? It does. So, and that would be 32. So that's going to be 32. 32 if I simplify. So 2 goes into 64 32 times. 7 pi over 6. Okay, does Does 6 and 32 reduce? They're both even, so I claim that this can reduce to 3 and this can reduce to 16. So we get that the area is going to be 16 times 7 pi over 3. Okay, so first let's figure out what is 16 times 7. Well, 10 times 7 is 70, and 6 times 7 is 42. So that's 112. Oh, oops, I forgot the 6 became a 3. So we get 112 in the numerator, 112 pi divided by 3. And there we are. It's an ugly number, but that's what it is. Sorry about that. That's what I get for making it up on the fly. Okay, let's do another problem. So example. So let's find the radius of a circle. So find the radius of a circle. Radius r of a circle, given that the area subtended, so given that the area A, that the area subtended by theta equal to, what angle did I use up here? Let's do 7 pi over 4. 7 pi over 4 radians is 14 pi square feet, so feet squared. Okay, so what do we know? We know that the area of a sector is 1/2 radius squared times the angle theta given in radians. 1/2 r squared theta, right? 1/2 r squared theta. Okay. So let's see what we have. I'm trying to find the radius, so that's what I want to find, r. But the area is 14 pi square feet. So I know I'll have 14 pi for the area. I'm trying to find the radius. And what was the angle theta in radians? 7 pi over 4. Okay, so now I just need to solve for r. So the first thing I'm going to do is to cross multiply. Let's first multiply by 2 so that I can reduce the 2 on the right hand side. So on the left, 2 times 14 is 28 pi will be equal to r squared times 7 pi over 4. So first thing I do is I deal with the fractions. So let's cross multiply again by 4. So that'll cross cancel that 4. Okay, now on the left, I'm just going to say 28 pi times 4. I'm not going to actually do the math, and you'll see why in a moment, is equal to r squared times 7 pi. Okay. Okay, so now I'm going to go ahead and divide both sides. What color should I use? By 7 pi. So whatever I do to one side, I do to the other, trying to isolate r. So on the right, of course, this fully reduces. But on the left, the pi's reduce, and 7 goes into 28 4 times. Okay, so now what do I have on the left? I have 4 times 4, which is nice. So 4 times 4, that's all I have on the left, is equal to r squared. Well, that's radius times radius, right? Radius times radius. So I claim that if I take the square root, the radius is 4, which is nice. So 4 is equal to the radius, and there we are. Okay, So I hope this makes sense, and I will see you guys in the next section.